Okay, so we're going to get into the topic of transition metal chemistry. This is a fairly short chapter. We really just want to talk about some features of transition metal ion, and then we'll talk about how these transition metal ions form complex ions with certain types of ligand. Transition metal, as you know, is the part of the periodic table that's highlighted here, which is this part right here, and it includes these two rows of the periodic table, which are called the lanthanide and the actinide series. For the top four periods in the periodic table, those elements are all D block elements that the last electrons to be added are added to the d orbital, whereas these two right here are f block elements that the electrons added there are added to the f orbital. We're really going to be mostly talking about the d block element and thinking a little bit about how these d block elements, particularly the first period of these D block elements, how those transition metals can form complex ions. The main thing that we notice about transition metals is that they don't differ as much as they go from one group to another. So if you go from this group right here to the next one to the next one, the difference between the properties of those transition metals are not as dramatic as compared to when you go in the main group elements, which is these green ones right here, right? So if I go from, say, carbon to nitrogen, or nitrogen to oxygen, or lithium to beryllium, for example, there is a sizable difference in chemical and physical property. The reason the transition metals don't differ by much is because you're adding the electrons to the d orbitals, which are the inner orbitals, to the inner shell, versus you're talking about the main group elements, you're adding to the valence shell. So the electrons are added because it's being added to the inner shell. The inner shell electrons are not really used for bonding, and so they don't affect the properties as dramatically as when you're adding to the valence shell, which is what happens when you're dealing with a main group element. Now, the other thing we notice is that the transition metal elements, they are able to form multiple oxidation states, right? So if you're talking about sodium, for example, which is a main group element, all sodium can do is just form sodium plus, or if you're talking about magnesium, can only form magnesium 2 plus. But if you're talking about, say, iron, simple case, you can form iron 2 or iron 3 plus, right? If you're talking about something like manganese, it can actually form quite a few different oxidation states, starting from +2 all the way to +7. So there's like a range of oxidation states that it could form. Typically, the maximum value of the oxidation state is when the electrons in the s and d orbitals are completely removed. And you can do that by just figuring out the electron configuration of all of transition metals. So they're shown in this table right here. As a reminder, you already learned how to do this in General Chemistry 1. So hopefully this is just a quick review. Something like manganese, if you look at it here, has 25 electrons originally. So if you go to the closest noble gas to manganese, that would be argon, right, which has 18 electrons. So then the other 7 would be the ones that you're filling up in that fourth shell, starting with the 4s2 and then the 3d5. Now, all those 7 electrons could potentially be lost, given away, in other words, and that's why at the most you can have a +7 for the charge of the manganese ion. At the minimum, you can lose just the 2 s electrons, and so the minimum is a +2. And then you can lose anything there in between. Now, when you go to the sort of the end of that part of the complex ion, so when you're going to something like copper or zinc here, the number of oxidation states start to decrease by quite a bit. So you can see that it kind of maximizes here in the middle, where you have many of these guys having multiple oxidation states. But as you get to the end, you only have usually one of them, and they're usually +2. And the reason it's +2 is generally because they're losing just that 4s electron. They're not really losing any of the 3d electron. And the reason for that is that there's actually a considerable increase in the ionization energy of these d electrons as you go further and further to the right side of the periodic table. And the reason for that is because as you go to the right side, of course, the number of protons increase, which means this quantity that we talked about in Gen Chem 1, Z effective, which is the effective nuclear charge of the atom, right, which is the charge that attracts all the electron, is getting stronger and stronger, and that makes it a lot harder to pull the electron out from the atom. And once you are able to pull one out, then it gets harder to pull the second one out, and then it gets harder to pull the third one out. So you can see here that the first ionization energy is fairly flat, right? Another way to say this is that it's pretty easy to ionize your atom to go from 0 to +1. But then when you look at the third ionization energy, you can see that the value actually ramps up quite a bit. So the first metal there, scandium has about a 25 electron volt. This is just a unit of ionization energy, but compare that to the last one, which is zinc, it's close to 40. So it goes up about like 70%. So it's a lot harder to pull that third electron of zinc. And that's why in zinc, the oxidation state at the most is just +2. You can't really get it any higher than that, just because it's so hard to pull that third electron off from zinc. So the main reason why we are discussing transition metal chemistry here is to talk about something called coordination compounds, which are basically compounds that are composed of two types of ion. One of them is a complex ion, which I've discussed it before. It's just a transition metal ion that is attached to a number of electron donors that we call ligands. And we'll talk about both of these in a bit more detail in a second. And then we also have a counter ion, which is basically just the ion that balances out the complex ion in such a way that you get an ionic compound throughout. So the difference between something like a standard ionic compound like NaCl versus a coordination compound is just that with NaCl you just have your Na plus and your Cl minus, but here you're going to have maybe a complex ion which has a positive charge, and then here you might have your Cl minus. That would be one type of coordination compound. You might have a cation like sodium plus, and you might have a complex ion on this one that is negatively charged. Okay, so that would be another type of coordination compound. So you can have both of them being complex ions as well, but basically any combination where there is a complex ion involved would be considered a coordination compound. So an example of coordination compound is something that looks like this. We'll learn how to name this later, but you can see here that there's a cobalt, ammonia, and then chloride, and all of these is written a square bracket, and so that represents the complex ion itself. What you want to see here is that this whole part right here is your complex ion, and then the part outside that would be your counter ion. So in this case you have two chloride ions there that counts out your complex ion charge in this case. So since there's two chloride ion, that tells me that the complex ion must have a charge of +2. Okay, and so if you break it apart, this is what it looks like. You have your two chloride ion, as I said here, and then here's your complex ion, which has cobalt as the transition metal ion, and then you have 6 ligands. You have 5 ammonia, and then you have 1 chloride serving as the ligand. And remember what that looks like is you would have your cobalt in the middle, and then you have something called a coordinate covalent bond, in this case 6 of these, and 5 of those bonds are to the nitrogen and ammonia, and then the last bond is to the chlorine, which is the chloride ion in that case. So that's the complex ion itself, and that has a charge of +2. Now, how do I get a charge of +2? I get that because each of the chloride, remember, is -1. Ammonia is a neutral molecule, so 5 of them will just give a charge of 0. That in fact tells me that my cobalt must be a +3 cobalt. Okay, and so that's how I get a total charge of +2. That's the reason why in the earlier part we had talked about how some of the transition metal ions can have multiple charges, and you'll see that depending on the type of ligands that are used to bond to the metal ion, you're going to have different charges for the complex ion itself. So coordination compounds actually is a good example that tells you how transition metal ions can combine with other species, right? The oxidation state of the metal ion, which is that +2 or +3, tells you how it's able to combine with other ions to form a neutral species, okay? And then the coordination number is the number that reflects how many bonds there are between the metal ions and the ligands. So for the example that we just looked at, which is this cobalt with ammonia and chloride complex ion, that one has 6 bonds between the transition metal ion and the ligand, so we would say that the coordination number is equal to 6 in that case. The coordination number usually will range from 2 to 8, and it's always an even number, so it could either be 2, 4, 6, or 8. I would say the most common one would be 6, and then you'll see either 4 or 2. 8 is not as common. You can't really tell, unfortunately, how many bonds will be formed between the ligands and the transition metal, because a lot of it depends on the type of the metal that's involved, the specific ligand that's involved, and just the type of electrons that are being used. So it's not so easy to predict the actual formula of the complex ion. So you'll always be given that information either in the form of the formula of the complex ion or some other information that will allow you to figure out how many ligands are bonding to that particular transition metal ion to form your complex ion. The structure of these complex ions are as follows. If you have a 6 ligand arrangement, or 6 bond, I should say, arrangement, then that's going to be an octahedral type of complex ion. You might remember this also from our discussion in Gen Chem 1 when we talk about VSEPR. When we have 6 electrons around the central atom, we have an octahedral arrangement. If you have 4, there's sort of 2 possibilities. If the 4 is maxed out as 4 and there's no other lone pairs there, then that's just going to be a tetrahedral arrangement. If the 4 instead originally start with lone pairs that are formed here, then that's going to be an actually octahedral arrangement that loses 2 of those bonds, which means it's just going to be this 4 right here. So that's what we call a square plane. If the complex ion only has 2, so something, let's say, that looks like this, then it's just going to be linear, as you might again recall from VSEPR discussion in Gen Chem 1. Okay, and I want to repeat again that the bond between the transition metal ion and the ligand is what we call the coordinate covalent bond. It's a different type of bond. It's not completely a covalent bond, but it's also not complete an ionic bond. So it's something in between. And that bond is actually formed by an interaction between the ligand. The ligand in this case is donating electron pairs to make that bond. And so the ligand acts as a Lewis base. Remember that a Lewis base is an electron donor. And then the transition metal ion in this case acts as a Lewis acid because it's the electron acceptor. So it's pretty much just a Lewis acid-based reaction. So the 2 of them come together and they form this complex. Now, ligands can be divided into different types depending on how many lone pairs are available on the ligand to actually make a bond to the transition metal ion. So if you have ligands where there's just 1 lone pair that's available, something like NH3, you can see that it only has that bond that's available, then that would be called a monodentate ligand. Okay, so water is another example of this. You might say, well, there's 2 lone pairs on water, but only one of those could be used to form a bond, because once it's used, the other one is not possible to kind of twist around to form another bond with the transition metal ion. There are ligands that are a little bit bigger, and then they have multiple atoms that have lone pair on the ligand, and those atoms are able to then form multiple bonds to the same metal ion. So if there's 2 of these, then we call them bidentate ligands. So here's an example. These are all the monodentate that I just mentioned earlier. The bidentate would look something like this. So this molecule right here is called ethylene diamine, or EN. A lot of times it's shortened as that. But the diamine here, each one of these nitrogen has lone pairs on them. So if you have a metal ion right here, then both of these nitrogen can make coordinate covalent bonds with the same metal. And so that's why it's called bidentate. A lot of times these bidentate ligands is also called chelating ligand. The word chelates refers to the fact that this looks like a claw, and the Greek word for claw is chele, and that's why they're called chelating ligand. You have also ligands that can form 3 bonds. So here's an example. So this particular ligand has 2 oxygen that has lone pair on them, and then nitrogen that also has a lone pair. So all those can form coordinate covalent bonds, 3 coordinate covalent bonds. This is a tetradentate example. In this case, you have 4 of these nitrogen. They're all coordinating the metal ion. And this one is actually a really complex one. This is a hexadentate ligand, where 6 of these coordinate covalent bonds are formed by the same ligand to the metal ion. Okay, this particular ligand is actually quite well known. It's called EDTA, ethylene diamine tetraacetate, and it's one of the ones that is often used as a metal scavenger. Actually, is what they're called, because they can, if you add EDTA to pretty much any kind of solution, it will just bond to all the metals. In other words, remove the metal out of the solution, just because it's so good at making these coordinate covalent bonds with any kind of metal.